Hi, in this video we're going to look at Argand diagrams and how they're used with complex numbers. Now, there was this French mathematician called Jean-Robert Argand who, while working with complex numbers, developed this way of being able to represent a complex number diagrammatically. Always useful to have a diagrammatic view of what you're thinking about. And basically he took the normal Cartesian plane that we're used to with its set of axes, and he split the plane into a real axis and an imaginary axis. So just as with the Cartesian plane, we'd expect the horizontal axis to be the x-axis, or the independent variable axis, and the vertical axis to be the imaginary the y-axis. So he split up the plane into a real component and an imaginary component. And then he said, right, if I've got a complex number, like the one that I've shown over here, 4 minus 3i, I can go and represent that using this plane. So the real part is this part over here, and the imaginary part is that part over there. So when I say that I have a real component of 4, it means I can go 4 along the x-axis. There's 4. And my imaginary component is of minus 3. And we follow the same conventions that we would follow with the normal Cartesian set of axes. Minus 3 would be below the horizontal axis. So this will go down 1, 2, 3. There's minus 3. So there's 4. Here's minus 3. And so this point over here is going to be my point for minus 3i. And we'll represent that with a line that goes from the origin down to that point. So that is a way of looking at a complex number using a set of axes like this. So that means that this complex number, which in general terms we can refer to as z is equal to a plus bi, that means that it has both length and direction. So if I say this is the point over here, a plus bi, and I go and link that up from the origin, I'm going to draw my line out to there. It's got a length, the length being the length of that line, how far away that point is from the origin. And it's got a direction, the direction being the angle that this line makes with the horizontal axis. Because we're using this sort of approach, we need to give these things names or titles. And so the length of this line, the distance away from the origin, we're going to refer to as the modulus of x, of z rather. And that modulus of z is going to be made up of two components. And if we realize that we're working with a set of points that are on a right-angled plane, we over here have a little right-angled triangle. This component up over here is b, that component over there is a, and so the modulus of this point, the length that is away from the origin, will be determined using Pythagoras, and it's going to be a squared plus b squared. So the imaginary component squared plus the real component squared, all inside the squared bracket. And I'm going to keep that as a positive amount because I'm dealing with it as a distance. Once we've done that, we will then need to think about the angle, the direction of this point, the angle that this line makes with the horizontal axis. We're going to call the argument. And the argument is basically going to be an angle, and that angle is going to be measured from minus pi through to positive pi. So in other words, from minus 180 degrees through to 180 degrees. So we're either going to measure it around that way, or we're going to measure it around this way. we keep those limitations on it. And how are we going to work out this angle? Well, we basically use a bit of basic trig. This is the angle that we're working with over here, and I'm going to call it theta for obvious reasons. And the argument of z basically is going to be the tan of theta. In other words, it's going to be tan to the minus 1 of b over a. That will give me the argument of the particular point, the angle that the line makes with the horizontal axis. Right, let's take some examples of this, and let's see what these look like with actual complex numbers. So I'll take a couple. I'll take the value z1 to be the point 3 plus 2i. I'll take the point z2 to being 2 minus 3i, and I'll take the point z3 as being minus 3 minus 4i. It would be useful to have a set of axes. So I'll just pop that in quickly. Okay, and so here we've got our set of axes positioned, and let's go about tackling each one of these. So if I deal with the first one over here, z1, it's 3 along the real axis. Remember, this is our real axis. This one over here is our imaginary axis. So I'm going to go 3 along the real axis, and I'm going to go 2 up the imaginary axis. There is my point over here. That is 3 plus 2i. And what we need to do now is we need to find the modulus and the argument of this. In other words, how far away from the origin is it, and what is the angle that it makes with the horizontal axis. So the modulus of z1, well, is basically based around this little right angle triangle over here. I know that my vertical distance is 2, my horizontal distance is 3. So the modulus of this is going to be the square root of 3 squared plus 2 squared. And when I do all that together, I'm going to get the square root of 13. And I'm just going to leave it as a surd like that. No, I don't need that. And then the second part is to look for the argument of z1. And the argument of z1 is simply going to be tan to the minus 1, the angle that this thing makes with the horizontal axis, that angle over there. And I'm going to use trig for this. It's going to be tan, which is going to be opposite over adjacent, so it's going to be 2 over 3. Tan of 2 over 3. And we get the trusty calculator for that. Shift tan of 2 over 3. And this is going to come up as 0.588. That's to 3 significant figures. Now, we generally write the argument in radians. Sometimes it'll be given in degrees, but generally it'll be given in radians. So there's your first point. There's the point Z1 in Argand, on the Argand diagram. And there is the point defined in terms of its modulus and its argument. The point Z2 is at 2 minus 3. Let's do this in a different color. So 2 minus 3. 2 is 2 along the horizontal axis. So that's to this point over here. And minus 3 is 3 down the imaginary axis. So it's going to be over here. So here is my point, 2 minus 3i. We get the line from the origin to that point. Do that. Let's just get. So I now need to work out the modulus of that. Well, that's going to be fairly similar to the modulus of the previous one. So I can say the modulus of Z2, once again, is going to be the square root of 2 squared plus minus 3 squared. And that's going to be the square root of 13. That's simple enough. And then I want to know the angle that this makes with the horizontal line, that angle over there. So the argument of Z2 is going to be tan to the minus 1 of the opposite side is going to be minus 3. The adjacent side is going to be 2. And so if I work out what that is on the calculator, shift tan and minus 3 over 2. And that comes up with the value of minus 0.983, going to 3 significant figures. I don't deal with it, let's make that clear, it's a negative number. I don't make that as an angle that goes all the way around in an anti-clockwise direction. I'm going to remember the argument of Z goes between minus pi through to pi. So it's going to go from here around to there. So I measure the angle backwards from the horizontal, and that gives me my value of minus 0.983. So I'm not going to bother with this last point. I think you should be able to see that that's going to be down in the third quadrant and easy enough to be able to plot from there. So hopefully this makes sense to you, how we go about representing complex numbers on the Argand plane using modulus and argument. Goodbye.